In this video, we'll study the kinetics of consecutive reactions. Now let us say this consecutive unimolecular reaction is given by this reaction A to form this intermediate I, and then this intermediate I forms this product P. Now suppose rate constant for this first reaction is K1 and a rate constant for this second reaction is K2. Suppose initial concentration of A, it is given by A0. Now for this reaction, the intermediate, it occurs in the reaction steps, but it does not appear in the overall reaction, which in this case is from A to P. So we want to study the characteristics of such reactions where product is formed through intermediates. Now we can write rate of decomposition of A as d A upon dt, and it will be equal to minus K1 into concentration of A. That's our first equation. Now this intermediate I, it is formed from A, but it decays to P. So rate of formation of I, it is given by di by dt, and it will be equal to rate of formation, which is K1A minus rate of decay, which is K2I, and that's our second equation. And finally, rate of formation of this product dP by dt, it is given by K2 into I. So we have three equations. Now this first one is a simple first order reaction. So we can write this as d concentration of A upon concentration of A, and it is equal to minus K1 dt. Now we integrate it from its initial concentration, which is A0, to concentration at any time, say A, from 0 to T. Now we can write this as log A minus log A0, and it will be equal to minus K1T, or from here we can say concentration of A is its initial concentration into e to the power minus K1T. So concentration of this reactant A, it is going to decrease exponentially. And that's our fourth equation. Now we'll start solving this second differential equation. Now here we are given that d I by dt, it is equal to K1. Now concentration of A is A0 e to the power minus K1T and minus K2I. Now basically this is linear differential equation in I. So we can write this as di by dt and plus K2 into concentration of I, and it will be equal to K1 into A0 e to the power minus K1T. Now this is linear differential equation in concentration of I. Now first we'll calculate its integrating factor. Its integrating factor will be e to the power integration of K2 dt. So it will be e to the power K2T. Now we'll start writing its solution. So this is I into e to the power K2T, and then this integral K1 A0 e to the power minus K1T into e to the power K2T dt, and we can write this as this I into e to the power K2T, and here it will be this K1 concentration of A0 and then e to the power K2 minus K1T dt. Now we write this as this is I e to the power K2T, and this is K1 into A0, and here it will be e to the power K2 minus K1T upon K2 minus K1 plus C. Now we know that when T is 0, concentration of I is 0. So we'll put that this is 0, and here it will be this K1 A0 upon K2 minus K1 and plus C. So value of C is minus K1 A0 upon K2 minus K1. So we can write this concentration of I e to the power K2T, and then we'll take K1 A0 upon K2 minus K1 common, and here it will be e to the power K2 minus K1T, and then minus 1. Now what we'll do is we'll take this e to the power K2T on the right hand side. Then we can write this as concentration of I, it will be K1 A0 upon K2 minus K1, and it will be equal to e to the power minus K1T minus e to the power minus K2T, and that's our fifth equation. So basically we have got concentration of A. So concentration of A at any time T, it is given by A0 e to the power minus K1T, and concentration of this intermediate I, it is given by K1 into A0 upon K2 minus K1 into e to the power minus K1T minus e to the power minus K2T. Now finally we need to find concentration of finished product P. Now we know that at any point of time, concentration of A plus concentration of I plus concentration of P, it is going to be equal to initial concentration of A. Now we already have A and I, so from here we can find concentration of P. So now we can write this concentration of P as this A0 minus, now concentration of A is A0 e to the power minus K1T, and minus concentration of I, which is K1 A0 upon K2 minus K1, and here it will be e to the power minus K1T minus e to the power minus K2T. Now here what we'll do is we'll take A0 common, so it will be this concentration of P equals concentration of A0, and then here it will be 1 minus, and we'll take these together, so it will be just e to the power minus K1T plus K1 e to the power minus K1T minus e to the power minus K2T upon K2 minus K1. Now we'll simplify this. Now we can write this as concentration of P equals concentration of A0, and this is 1 minus, and here it will be K2 e to the power minus K1T minus K1 e to the power minus K1T plus K1 e to the power minus K1T, and then minus K1 e to the power minus K2T. Now here these two terms, they'll cancel, and we also have K2 minus K1. So from here we can write concentration of P equals concentration of A0, and then 1, we'll take this minus inside, plus it will be K1 into e to the power minus K2T minus K2 into e to the power minus K1T upon K2 minus K1. Now this is the concentration of P at any time T. So we have worked out concentration of A at any time, concentration of this intermediate, and concentration of this product P. Now what I'll do is I'll punch in some values in Desmos and we'll see what's the relationship between the three graphs. Now this red graph, it represents decay of A. So this A, it decays exponentially. Now this intermediate I, initially it's 0 and then at some point it'll be maximum and then gradually it'll decay to 0, and this product, it starts from 0 and it grows exponentially like this. So this is how reaction proceeds for consecutive elementary reactions. Now here we have taken this A as K1 and this B as K2. If we change the relationship between A and B, we'll get, but then characteristics of this equation will remain more or less the same.